Okay, everyone, welcome back. So now we're looking at the week 2 problem, and things are a little bit more involved, but still we rely on our knowledge of kinematics to solve these. Okay, let me read the question for you. John and Meg begin driving at the same instant, but at different initial positions. John starts off at a distance d miles to the west of Meg. John drives east with a speed of 60 miles per hour, and Meg drives west at a speed of 70 miles an hour. 1 hour after taking off, John passes Meg. After seeing John pass by, Meg drives an additional 80 miles when she suddenly decides to turn around to try and catch up with John. Meg drives east at a speed of 80 miles an hour until she catches up with John. Okay, so a lot of stuff going on there, but we will break it down piece by piece. Important not to get overwhelmed in these with all that's happening here. We're just going to do it step by step. So part A tells us to sketch a position versus time graph for the motion of the two drivers from the time when the driving starts until they pass for the second time. On your graph, make the west direction positive. Okay, so that's important. In general, you're allowed to pick either direction to be positive that you like, unless the person asking the question is insisting on one direction or the other being positive. I would usually pick east to be positive, since east is represented on a map to the right, and right is often what we pick to be positive. But here the question is specifically telling us the opposite, so we got to remember that. Okay, so part A. And keep in mind, when we're drawing this graph, we're not really too interested in making sure that it's to scale, or even what you'll see later is we might not even care that whether we figure out exactly where they pass. You know, it'll end up being, because I've done this problem before, that they pass when they pass for the second time, they're very close to the zero position, what I'm going to define to be zero. But that's not really relevant. The general shape of the fact that first Meg goes in one direction, then she changes direction, and then also how John is driving, those are the important aspects. The qualitative shape of the graph is important here, because we're basically doing this part A, even though it's part of the question. We're really doing it because we're going to use that sort of general shape to set up our thinking process when we're going to solve part B, which is where we get into the actual numerical solution. Okay, so let's see. Let's start from the beginning. So John, at the start, John starts off a distance d miles to the west of Meg. Now, west is the positive direction, so in this, I guess I can label that west is up, and this is time, the time axis along the horizontal. If John is starting off to the west, his position will start at some positive value, and I'm just going to define Meg's starting position to be 0. All right, that's my definition of my axes. Free to do that. I could make other choices, but this is what makes sense to me. Now, it says John is going to drive east. So John is driving east. That's in the negative direction, so his line is going to go down something like this. Meg is driving in the western direction. That's upwards. And they're driving at different speeds, but I'm not going to worry too much about getting the slopes exactly right to represent those speeds. I just want to generally say that John is going to go down. I'm going to call this, I'll just label it with his, oh, you can't see that. I'm just labeling the line with a J for John. And Meg is going to go the opposite direction, positive direction. They're going to pass, and then after they pass, she's going to go an additional 80 miles. So since I'm not labeling my positions or anything, I'm just going to make a line. It doesn't matter that whether this to scale would represent 80 miles or not. I'm going to just draw a line continuing in the original direction of travel. And then she turns around later, and she's going to drive until she catches up with John again. Now, one thing that is important is that her speed, after she turns around, is going to be larger than John's speed going away, which is important because that's the only way she'll catch him. Right? So, in other words, the line going down now has to be steeper than the line I've already drawn for John. So, and other than that, it doesn't really matter how I draw it, so I'll just draw it like this. So this is, what's her name? Meg. Meg's line. See, like that? Okay, so now I want to start labeling things, giving some variable names to the different points of interest on this graph. So I'm just going to define T1 to be the time that they passed for the first time. I'll define T2 to be the time when Meg finally turns around. And I'll define T3 to be the time when they meet up for the second time. Notice I'm labeling stuff along the time axis. Along the distance axis, I'll have to do a little bit more work to figure out all the distances, but I do know, for instance, that like this is a point of interest, so I'll just make a little dotted line there, and then this might also be a relevant position. So as I get some numbers, I might fill this in more, but for now I'll just... And that's sufficient for, in terms of sketching position versus time graph for the motion. This is all I really care about, not necessarily getting everything exactly to scale, just drawing the general shape to help me label things. Okay? So now we can move on to part B. So part B, the first part says, what is D, the initial separation of John and Meg? So we want to find, in other words, if I label on my drawing, we want to find this distance, the initial separation. Right? Okay, so B. What do I know? If I go back up to the question, hopefully you can read that. Whoa, this tripod is really unstable. Let me try and stabilize that. So the question, the relevant information here is that John starts driving with a speed of 60 miles an hour and Meg starts driving with a speed of 70 miles an hour. They're driving towards each other, and 1 hour after taking off, they pass each other. So if you like, there's a lot of different ways you could solve this. The most systematic, perhaps, would be to say that the position of John as a function of time is equal to his initial position, which in my graph, notice, Meg's initial position is 0, John's is D. That's why this graph is going to help me. So John's initial position is D, but he travels at 60 miles an hour in the negative direction, that's why this negative sign is there, times 1 hour. I'll just label it T for now, and we'll plug in the 1 hour in a minute. Position of Meg is... she starts at 0 and she's moving in the positive direction, so at 70 miles an hour, so her position is just 70 t, and then I know that at t equals 1 hour, position of John equals position of Meg, which tells me that d minus 60t equals 70t, which says that d equals 130t, where t is 1 hour, so d is just 130 miles. The other way I could have done this is to realize that if Meg travels at 70 miles per hour west and John drives 60 miles per hour east, then effectively they've got a relative velocity of 130 miles per hour, just adding the 60 and the 70, and since they meet after 1 hour, that means their initial